Hello everyone. So we are starting our plasma class again. What we are studying in these days is plasma sources. And in your previous class, we have studied about the arc plasma devices and how we can increase the power by changing the configuration of the arc device. So it is not possible to break a very large gap initially. What we can do, we can configure the device in such a way that we break uh, part by part. So initially we break a small gap, then we elongate the arc, then further elongate the arc, and finally we get our final configuration, which gives a pretty good length of the arc and a pretty high voltage drop because we are operating with constant current. So V into I is the power, and you get your, the final configuration on which you can operate. So in this class, we will be dealing with a bit more details of these arc devices. So this is how one actual arc device looks actually. The thing that I was telling you, the segmented kind of structure. So what you have seen over there is that there are three switches, CT1, CT2, CT3. I will just show you over here. So these are actually the CT1, CT2 and CT3, and this connection is the cathode connection, and the final there will be one anode connection. Okay. So this is the kind of device segmented, and what is there actually, if you want to increase the length of the such a device to increase the length of the arc, so then you need to separate each of the segment. Like you see here, the red one basically the copper segments, and they are separated from each other using some spacer. They are Teflon spacer, this yellow colored. And finally, what you are getting, actually you are breaking the gap initially between the cathode and the anode using this high frequency, and then you are gradually shifting this arc from one electrode to another with the help of a contactor, which are not shown over here. So uh, so this is the typical configuration, and the cathode, what I was telling you, that is a cylindrical cathode with a flat or a conical tip here. So this is the cathode tip. Here you are using a flat tip, and there is a conical section over here, and this is the cathode, and this is basically made of copper, although it is painted, so you are not able to see that. So this is inserted in a copper matrix, and these are cooling tubes which are cooling internally this copper, and that way it is cooling the cathode made of tungsten. Okay. And depending on the gas, as you have seen, that the plasma jet length, temperature, and instability behavior, all this varies. So here you are seeing visibly this is a nitrogen plasma jet and this is an argon plasma jet. You can see the differences in this in their features. So arc plasma devices, how they operate, and how they look, just to give you an idea, I have just shown it over here. So this is air plasma and this is argon plasma, and you have seen over here this is the nitrogen plasma. So you can see that as we change the composition, the plasma feature varies, and in the electrical discharge regime, this is the regime of the arc where you are seeing a negative VI characteristics. Now, the general understanding about how the arc operates is that there is a cathode and there is an anode, and this is emitting electrons which are finally entering into the anode, which is at positive potential. The current lines goes like this. So it is not a single path, there is a distributed zone through which the current passes. Now, the plasma forming gas goes through this region and they enter and then they form the plasma jet. Now, typical diagnostic looks like this, and if you want to confirm whether there is an arc route, the point where the current comes out from the anode, rather in other way we used to tell that the current enters into the anode, rather, but in correct way to tell that current actually direction comes out from the anode and enters into the cathode. The electrons are entering into the anode. So anyway, the junction where the current joins with the anode actually. So that is a very very tiny spot, maybe few millimeters square, and that spot is called the arc root, because this is an arc and that root actually moves very dynamically over the anode wall. So this is the anode wall, and it can be here, it can be here. So this is the axial movement, and it can rotate peripherally also. So all sorts of movement possibilities are there, and that is actually good for health of the plasma torch, because if it stays at a particular point, because so tiny spot through which you are passing some hundreds of ampere current, so it easily the current density will be of the order of 10 to the power 8 ampere per meter square, and that can easily melt the electrode. So to find a proof of that, you can go for this kind of arrangement. So because very high temperature, so you cannot directly look into this, so you can have its image over a metallic reflector, and then you can look at the reflector using some camera somewhere placed a distance away, so that the camera doesn't get affected by the thermal flux that is coming out from the torch. So this is just, we will be discussing more on this in the tutorial, and this how the current jets current configuration that comes out from the such arc devices. I have already shown you in the video direct capture of the arc root behavior. It is over here. I don't know, it was actually supposed to be a video that I will show you in the tutorial. So the different modes of instabilities that can originate in that, there are 3 different modes in which arc operates. So one is steady mode, one is takeover mode, and one is restrike mode. I'll just tell you what are these modes about, but I will not go into details. Those details I will be discussing in the tutorial. So here what I am showing here, a mode of instabilities in arc, where the arc voltage vary in a very regular oscillatory fashion. So this mode is usually called takeover mode or oscillatory mode. In another case where you see that voltage is staying constant, you look at this one, it is almost steady voltage you are seeing over. So this kind of mode occurs when the arc root stays at a particular point. So that time the voltage doesn't vary, or the arc length is also not varying. Actually, one thing you should understand here is that when you are having this kind of arc length can vary if this is dragged downward by the aerodynamic drag force, then the arc length will vary. Or if this arc root moves over this anode surface, then also the arc length will vary. And if it even rotates, then also it may happen that there is a mild variation in the arc root. So suppose this arc root is moving up and down in a regular fashion, then you will see the takeover mode kind of instability like this one. But when this arc is moving, staying at a particular position, and even the aerodynamic drag force is also balanced by the electromagnetic body force and keeping the arc configuration nearly steady, that time you will see the voltage is more or less constant. And there are other mode where you will see that arc is elongating, and then suddenly breaking at some upstream point. So there you will see this sort of kind of behavior. When you are operating such arcs at a very high power, and if you are operating with say molecular gases like say nitrogen, oxygen, or air, then usually this restrike mode of instability is very common to be found in such operation, okay, in these devices. So what we are finding there, that there are 3 types of modes of operation of arc devices. One is your steady mode, where the voltage remains more or less steady. One is your takeover or oscillatory mode, where the arc voltage oscillates in a very regular fashion. And there is a third one which is called restrike mode, where a sawtooth kind of behavior is observed in the arc voltage. So we will be discussing about various forces that can operate in this arc plasma devices, the electromagnetic body forces. So we will go in detail in the tutorials that will be coming up. And then now I should tell you the arc connection configuration. There are 2 types of arcs you will be hearing in this technological areas. One is called transferred arc and one is called non-transferred arc. So what are they actually? So I have shown you one configuration where there is a cathode, there is an anode, and the arc is established between this cathode and anode, and a plasma jet is coming out. And this plasma jet is used for different kind of applications. One application I have shown you, that is the plasma spray coating development. So when you are going to do that, then you are taking this configuration, and you are injecting some powder over here that is getting melted in the plasma jet, and that is spraying over the job. The coating is getting developed. Now here you see that no current is extending into the plasma jet. So this plasma jet is current free, and whatever heating is happening, that is happening within the device, not coming outside the device. Okay, so this kind of configuration where the arc is between the cathode and the anode and not connected to the job. The current is not transferred from cathode to the job. So job, there is no current is there. So this kind of configuration is called non-transferred arcs. On the other hand, when the current extends from cathode to the job, for example plasma cutting, there you directly connect the current to the job which is being cut. Okay, or you say melting furnace, there you connect the arc directly from the cathode to the material to be melted. So those kind of configuration where the arc connection is between the cathode and the job, those are called transferred arc configuration. So what you understand here, you get two kinds of arc connection. One is called transferred arc, one is called non-transferred arc. In transferred arc, the current extends from cathode to the job, and in non-transferred arc, the current doesn't enter into the job. So it is between the cathode and the anode. The plasma jet is current free, and in transferred arc, the plasma jet contains the current. Okay. Now I will come to another concept in arcs, which is called diffused arc and constricted arc. So what do they mean, and what are they, how they are formed? So here I am showing, this is the cathode, and this is the anode. What is their surrounding region? Now you see here that this cathode is emitting electrons, and your anode is receiving them, right? Now at the bottom, what I have shown here, that the central one is the cathode tip, and the surrounding blue one is the anode. I have taken 4 points, 1, 2, 3 and 4, just 90 degree apart, and I am asking you, suppose one electron is emitted by the cathode from the center, then where will it go? As a physicist, you know that all the points 1, 2, 3 or 4, they are at same potential, because they are made of copper in most of the cases, and copper is a very highly conducting metal. So all the points 1, 2, 3, 4 will be at same potential. Now the electron is emitted exactly from the center, so it is confused where to go, but single electron and it can go to single place. So where it will go? So you are also now puzzled where it will go, because it can go to 1, it is equally probable, 2 is equally probable, 3 is equally probable, 4 is equally probable. But the thing is that it is one electron, it has to go to only one place, it cannot go to all the places simultaneously. So that is a problem when we are thinking of a single electron. But when you are thinking of number of electrons, say of the order of 10 to the power 20, 10 to the power 22, number of particles, then what is happening, per meter cube, of course, then we are getting that each of them has some probability rather has equal probability to go 1, 2, 3, 4, and what will happen finally, you will see that same number of electrons, almost they are equally distributed among all along the periphery of this, this anode. So if that is the case, then what you are getting, that whole region is uniformly connected by the electron flow uniformly all over. So they are basically making a hollow cone shape, and they are getting connected to all over the anode inner surface uniformly. So when this is the kind of configuration, then we call it a diffuse star. But there are cases when, especially at higher current, when you are passing a very high current through the gas, then it is of course ionizing the gas, and then it is forming a plasma. Then what is happening, this current, it is producing its own magnetic field, okay, and that magnetic field, with along with the current density J cross B force, tries to pinch it. And this is a very flow driven region, because gas is coming from this zone, this blue zone, from the top, and they are disturbing, and there may be fluid dynamic instability. Suppose due to certain reason one region is getting bit colder compared to the other region, so the conductivity will be less over there, so current will not try to pass over there, so they will try to pass through the region where conductivity is higher. So the current, more current will be going there, more heating will be there, and they will be getting further higher conductivity. So the less region where the conductivity is low will be heated. So the non-conducting region where the colder places are existing, there will be more and more. Finally, there will be a very specific channel through which the current will be passing. So rest of the region will be having some colder regions, and the arc will not try to pass through that, because the arc will always try to find a path which is having very high conductivity, and that conducting region is like an arc which is connecting the cathode and the anode. So you will get a very constricted connection at a particular point. So this type of arcs, where the arc is not connected all over the anode periphery uniformly, rather it is connected to a particular point over the anode, that is called your constricted arc. So this is the constricted arc configuration. Now I will tell you about another important thing in arcs in such devices, that is called cathode and anode jet formation and electromagnetic pumping. So here I am showing you one actually practical example of this jet formation in arcs. You are seeing here, this is underwater, this is the cathode and this is the job. When we have established an arc between these two, and the electromagnetic pumping is basically forming this plasma jet inside the water. This is the very strong jet comes out from there. And how it happens, this is the cathode, and you see this is the transferred arc, and the arc is connected over here. Usually what happens, where it connects, a small male pool is formed over there, they can get solidified once the arc moves away from that place, because these anodes are usually very intensely cooled. These anodes are very intensely cooled. So once the arc moves from here to another place, this pool, melt pool, will be solidified and will be staying there. Now what is happening, this arc is getting expanded as it moves up from the anode. Okay, so that is making a cone-shaped configuration of the current density vectors. If that is the thing, then the magnetic field is like this, and here you see here that when this is the case, there will be a thrust generated. J cross B will be normal to this conical surface, and there will be a radial component in this direction, and there will be a vertical component in this direction. Radial components, you can see from here that they will cancel each other, because this force is all over this periphery, and they will cancel each other, because for each component that is moving one direction, there is exactly similar component from the other side which will cancel. So there will be net upward thrust, and that will physically make the plasma to move upward. Okay, like this here, what is happening over here. So what is then doing? Then when the plasma moves up, then it drags the colder region inside. Okay, whatever the gas that is staying there in the colder region, they will pull inside. So the cold plasma is coming, cold gases are coming and entering in the plasma, is moving up. Okay, so that what it is causing. So this is a kind of pumping which is induced by the J cross B force that is acting over here. So that is called J cross B pumping. Now you see that how this happens near the cathode. So you can see our typical configuration. This is the cathode zone, this is the anode zone, and both of them are intensely water cooled. And this is the zone where from these electrons are getting emitted. And you have seen in our simulation that the current density vectors goes like this. So here you are seeing that the J cross B force is having a downward, net downward force, and similarly at the bottom like this one there will be upward force. So the cathode the configuration J cross B configuration will put a net downward thrust. So that will cause the plasma to move outward from the cathode in the form of a jet. So that is called cathode jet. Similarly, over the anode, this is the anode jet. So in a torch, suppose it is a transferred arc, a jet will be coming from the cathode, that is cathode jet, and a jet will be formed from the anode at the bottom, the job. So both these jets, cathode jet from the top and anode jet from the bottom, can collide in between and make it spread in the mid zone. So this inverted bell shape at the bottom and bell shape on the top, so they are basically the cathode jet and anode jet, and this special structure that is formed is because of this J cross B pumping effect. Okay. So thermionic and thermochemical cathodes I will be discussing now. So how they are. So you have already seen the cathode, what was there in our previous class. There is a tungsten cathode inserted inside a copper matrix. Whenever you are going for operation with argon, there is no problem, because argon is an inert gas and it will operate fantastic. It has a very high melting point. This melting point is 3422 degrees centigrade. Okay, and it has very good thermal conductivity, has very good electrical conductivity. So together with all this, a thoriated tungsten, thoriated because to bring down the work function of these cathodes so that it can emit electrons very easily. So tungsten as a cathode works fine for inert gas environment. So these are called thermodynamic cathodes because when they are heated they emit electrons. Now this type of cathodes, when they are operating with oxidizing environment like say oxygen or air, then immediately they react with the oxygen in air or in pure oxygen, they form tungsten oxide. The moment the tungsten oxide is formed, its melting point is only 1473 degrees centigrade. You just note, melting point of the metal is 3422 degrees centigrade, and when it becomes oxidized, its melting point reduces drastically. It is just 1473 degrees centigrade. So almost the melting point has reduced by nearly 2000 degrees centigrade. So that is a tremendous drop. So the moment you want to operate this kind of devices having tungsten electrode in oxidizing environment, tungsten becomes tungsten oxide and its melting point reduces drastically, and it just takes few minutes to get melt and flow away. So after operation of exactly 3 minutes, what we observed here, this is the actual photograph. This is an actual photograph, and you see here this cathode was inserted and it has completely formed tungsten oxide, and it has come out like this because it is molten, and then when it flown out it solidified, and this is what we obtained. So this kind of cathode cannot operate with oxidizing environment, but they are fantastic cathodes, works fantastically for inert environment. Like even it can operate very well with nitrogen as well, and it can operate with helium, it can operate with argon, and any inert gas it can operate with. On the other hand, if you want to operate some arc device in oxidizing environment, then there are electrodes. What has been found that hafnium and zirconium are the best candidates probably for operating such devices. This is because you see that hafnium is having a melting point of 2230 degrees centigrade. Okay. But the moment it get oxidized, its melting point becomes 2758 degrees centigrade. So there is a rise in your melting point by around 500 degrees centigrade. Unlike tungsten, where you got a reduction by 2000 degrees centigrade, here you are seeing an increase in melting point by some 500 degrees centigrade. So this type of cathodes which reacts with the operating gas while operation and sustain the arc production. So that is, this type of cathodes are called thermochemical cathodes, because when they are operating with the plasma gas at very high temperature, they react with the gas and form some compound which helps them to sustain the arc at for longer time, because here the melting point is increasing, so that reduction in melting point is not there, and you really want to operate with oxygen because that will help you to increase the melting point. So that is how the thermochemical and thermionic cathodes operate. So I will be more about this in tutorial. I will be telling that what are the different properties of ideal electrodes there. Then I will be showing you the real cathodes, what are the challenges them, and then what is the rate of erosion when they are operating in a molten form at the tip. Then I will show you some actual pictures, and really how a cathode which is operating in molten state can operate for tens of hours without any issue. So what is the science behind, I will be explaining them in the tutorial. Also I will be telling about some special cases of arc motion defying apparently defying the normal force notion. So that I will be discussing. This is called retrograde motion in arcs, which are contrary to the conventional concept. So that I will be explaining in the tutorial. I am not going into that. Rather, I would like to discuss some of the very important aspects of operating such devices is the power supplies. So arc devices are usually operated with constant current power supplies, and usually IGBT based constant current power supplies are nowadays used. Earlier, SCR controlled silicon controlled rectifier, that SCR stands for. So this kind of power supplies are used, but ripple was quite high in those. But in recent time, IGBT based insulated gate bipolar transistor, so IGBT stands for, IGBT based current supplies are being used, and they can offer you very high stability, very less ripple, constant current power supply. Um, Usually the open circuit voltage in these devices is usually taken twice the operating voltage. This open circuit voltage is required to ignite the arc initially, so that the moment you cause a breakdown, that potential that you apply across the cathode and the anode, they can make the arc to sustain. Okay, so this is the VI characteristics of arcs, and there are certain characteristic, this is the VI characteristic. So current is constant over a wide range of voltage, and this is the negative VI characteristic. So this is the one which you are familiar with. So this is current is increasing and the voltage is decreasing. So the solid line is for the arc characteristics, and this dotted line is for the power supply characteristics. So I will be back in the next class with this power supply characteristics of arc devices, and what are the stable and unstable operating points in arcs. So this much now. We will see you in the next class. Okay, thank you.